is 800 volts. Then it's released and it falls back. So first we got to find the work done to bring it to the positive plate. Okay, so the work formula. So work done by us, our pulling force, will be that pulling force acting over a certain displacement through the field. It's positive work because the displacement is in the same direction as the force, as our applied force. So this is known. This is what we're interested in finding. We've got to find that positive force first. So if we're, what's an expression we can use to find that force?
FE is equal to F.
Okay, good. So that pulling force is equal to FE. By Newton's second law, they're balanced. And what expression can we use to find that pulling force? We have a charge being pulled through a potential difference. What's the unit? What's that? Q times V. And if you don't remember that, remember this. That's a coulomb, right? What's this? Which is what per coulomb? Not newtons per coulomb, that's electric field. Joules per coulomb. Yeah. This is the electric potential energy given to a charge per coulomb, right? So if you got a 1 coulomb charge, you get 800 joules in that. You got 2 coulomb charge, 1600 joules. You got half coulomb charge, 400 joules, right? Okay, so what happens when you multiply coulombs by joules per coulomb? What do you get? Joules, which is work. So remember those units, and you'll remember the formulas as well. Okay, so this is given, and this is actually, we'll call this delta. This is delta. And this is given. So now this is known. So we can solve. And that will be part A. Part B, calculate the magnitude of the average force required to do this work. Okay, I thought we already did that. It's just that, once we screwed something up here. How else would you have found that? Anyways. Part C, calculate the kinetic energy of the pith ball when it arrives back in its original position. Okay, so now the situation's changed. Now we've got a pith ball, which is at the positive plate and is allowed to accelerate. So we need to figure out the speed of this pith ball once it arrives at its original position on the negative plate. All right, so what do you want to do here? Okay, we can use conservation of energy, or we can use work energy theorem. Which one do you want to do? Since we're already dealing with work here, to me, work energy theorem seems more intuitive. So the work done by the electric field, okay. Now our displacement's in this direction. The work done by the electric field will be the change in the kinetic energy of the particle, the pith ball, actually in this case. All right, so we put a certain amount of energy in. Just like remember the elastic, we put the energy in. When you release the elastic, all the energy that you store in the elastic is released. Because we're talking about 100% efficiency, no thermal energy produced here. So in this case, we put all this energy in by drawing the charge to the field against its will. Then we released it and it snaps back, just like an elastic. So how does the work that we do compare to the work that the field does on release?
It's less than?
Well, what happens if it was less, then there would be energy left over. Is there energy left over?
No.
Is there thermal energy?
No.
No, so they've got to be equal, yeah. So that means this is known. So the energy that we put into the pith ball field system is stored in the system by virtue of the fact the pith ball is on the opposite plate. The plate doesn't want to be on, right? Just like an elastic, it wants to snap back. As soon as you release it, it's going to snap back to that negative plate. So it's going to release all that energy that we put into there. So that means we know this value, and we know this would be 1/2 mv2 squared minus 1/2 mv1 squared. This is the change in kinetic energy. Where of course this is 0 because this thing starts from rest. So now this is known, and we still. You could also draw the energy bar graphs and use conservation of energy. It would just be full conversion of electric potential energy to kinetic energy, and you would get the same equation in the end. Part D, well, this is part C. A and B are both there. Part D, calculate the speed of the pith ball just, oh. Yeah, okay, so this is part C. You would just solve for this, and then you would solve for the speed for D. So when you think of these charges moving through the field, just think of an elastic being released, although in this case the force is constant, in the case of elastic it's not, but just think of an elastic being released, or the best analogy is just think of, you've got an object, okay, so this is the negative plate, the ceiling is the positive plate, this is a positively charged object. I move it through the field, and when I release it, it snaps back to the negative plate. That's all it is, right? We're talking about gravity, but you would not, this question would be a piece of cake if we just rotated it and pretended it was gravity. There's no difference between they're both just fields, right? So again, this is a positive charge. This is a negative plate where it wants to be, just like an object wants to be on the ground. The ceiling is the positive plate. It doesn't want to be up there. It's going to fight me the whole time I raise it, just like an object fights being lifted, right? It tries to resist it. And then as soon as you release it, it wants nothing more than to snap back to its lowest energy position, which is on the ground, or if it's a positive charge, on the negative plate.